talk about, stuff to ask about. Let's take a few minutes to come into the room. Get here. Leave behind what was out. Leave behind our puzzles and our planning about bands or whatever was going on. I don't know what's going on. Noticing probably your body's a good place to start. Bring ourselves back, noticing the sounds of Nathan's.
Sorry about that.
It's really okay, my friend. Yeah, I appreciate you tried your best to just be innocuous, but then I heard Grace giggling. I knew the show was over. All right. Oh, Morgan, will you stop by her after class just real quick? I just want to give you some stuff back. Yeah. That was just one of my notes. Couple things. Quiz 3 next Wednesday. It's on the calendar. What will be on it? It's mostly going to involve reading ahead. I would probably start this weekend doing that. It's really section 3.3 and 3.4. But just some of the basic highlights there. We'll go through the nitty-gritty together. With some basic definitions about Mobius transforms and the Riemann sphere, and a few problems to work that I'll make sure to get you solutions to that we'll talk about as much as you would like. And then we've got a homework that's sitting around. How's that going? Does anyone have questions on the homework? Anything you'd like to talk? I made a little note to myself here. It said, if no questions on homework, that's a problem. So we have a problem. Okay. Oh yay, there is no problem anymore. You fixed it.
So for the very first one, I know we did an example in class of finding the image of a like y equals mx plus b under inversion of the unit circle.
Yes.
The first step from the equation to getting your x and y,
Yes.
I think I followed in the book, but I'm not 100% sure.
So you're talking about moving from the xy equation to the z bar equation?
Yes.
Cool. You are not the only one who has a question about this, so let's talk again. So, convert an xy equation into a z bar equation. Let's talk about how to get those substitutions first. So the thing is, this is our relationship that takes us from xy to z. So I can write z conjugate, it's just that. And then none of this shit, there's like nothing to really argue about or be baffled about, I think, and I hope this isn't baffling. Add straight down. So z plus z bar equals 2x. These die off, they cancel. And now I can solve for x by dividing by 2. So 1/2 z plus z bar is the substitution for x when I see an x. In a similar way, I can subtract these two equations and kill off the x's. So when I subtract them, I get z minus z bar equals x minus x, dead. Iy minus iy is 2 iy's. Divide through by 2i. Get this, like so. And then I like to just move that I up, so multiply the top and the bottom by minus I, or realize that if you move it up on top, it just becomes minus I. So then these are my substitutions, so that if someone asked me to take the equation x plus y equals 1 and convert it into the z bar form, what I'm gonna do, and this is what you're asking about, right, Kitra, before I keep going? Okay, cool. I'm just going to replace x with this expression. I'm going to replace y with this expression, so it becomes minus I over 2 z minus z bar equals 1. And then I'm going to group together by z and z bar and use those as my signposts. So this becomes, let's see, we have half a z minus half an I z from there. And then plus half a z bar, minus, which is plus half I z bar equals 1. And if I really wanted to get that into the form our book uses, I'll just move that 1 to the left like that. And I'm good to go. And notice how I've got an alpha here, z, and then its conjugate, alpha bar, right there, z bar. So I know it's the line equation. Does that help?
That makes, yes.
Good. Awesome. Good question. And I don't think there's any others, if I recall correctly. All right. All righty, my friends. When's that homework due?
On the calendar, it says next Wednesday.
Yeah, that's what I was gonna, that's a good, yeah, I just looked at that. The calendar says next Wednesday. I think I probably said Monday, but I'm starting to think Wednesday's the day that it should be due, so that we can talk on Monday. Please, please, please get into these problems by Monday. Please start every single problem. This stuff is not light, and it takes a bit. And then you got some stuff for the quiz to work through too, so get cracking, my friends.
Sections, did you say were the quiz?
It's all kind of listed in the thing on the calendar, Christian, but it's essentially section 3, 4. Some highlights out of 3, 3, 3 and 3, 4. Yes, 3, 3 and 3, 4. Awesome. Yeah. Some of it's definitions, some of it's simple problems to solve. Okay, let's review. Let's just kind of let's pull together some things that we know and refresh our collective memory about inversion. We're going to spend quite a while on this. Certainly today, we'll probably still be talking about it on Monday. I've got a feeling. So everybody did pretty good on the quiz. That's great. Everybody, at least at that point, knew what inversion was, and they did a great job explaining it. So inversion is with respect to a circle, and we take a point that's in or outside of the circle. Let's see, this one's radius r, and I somehow flip it over the circle, and we have a formula for that. Inversion with respect to the circle C of a point Z, and that Z could be outside as well, is equal to the center plus the radius squared over the difference between this point and Z naught the center, bar. And everybody got that formula right too, so that's cool. So we know that. And then this is called Z star. We use that star notation to indicate a flip, an inversion. Z and Z star are said to be symmetric with respect to the circle. So WRT is with respect to the circle C. Cool. So it's a reflection of sorts. It's actually very analogous to flipping over a line. So if I have a line L, this is a circle, this is a line, they're both clines. If I flip the point Z over this line, if I reflect it over this line, if I invert it over this line, it's literally just the reflection onto the other side. So you take this perpendicular, and these two distances are equal, and that's the Z star if I'm reflecting with respect to a line. We'll get to see that this is really just this, but with an infinite circle, an infinitely large circle. That'll make sense after you do some reading for next Wednesday and look at the Riemann sphere and Mobius stuff. So let's see, I wanted to see, what are our other things we know? So that's our basics. If we have the unit circle, so if C is the unit circle, and that means it's centered at the origin, then Z star is 1 over Z conjugate, just nice, clean, and simple. It's really just that formula with R equals 1 and Z naught equals 0, so it's nothing super shocking. We also know that inversion takes clines to clines, sends a cline to a cline. And I want to talk a little bit about that right now. So it takes a circle or a line to a circle or a line. Let's get a little app up here, because it's so much better than being drawn. And I've got this app available for you. I put up a new app as well for the stereographic projection. It's a really, really sweet app. And you can enjoy that or not. I hope you do. Cool. Let's get this up. I think I put this app in there. A little mood lighting. Oh, that's much better. So much better. Okay, Regis computer, do your stuff. Wow, you did it. Congrats, Regis computer. So, this is an app that lets us see inversions of points, lines, circles, or polygons. The polygon's really fun because things look funky under inversion. So this formula here, what do you think that's saying? What is this OP times OP prime saying? It's not real obvious, probably because I got some of the stuff hidden up there. What are they talking about?
Is it the Z minus Z naught or something?
That's it, exactly. So it's that fundamental definition of inversion that says, if I've got a circle, I guess I could have put this in the list of things we know, and there's Z naught, and I want to invert a point Z, I draw a line from the center to the point I want to invert, and then I'm looking for the point Z star out here on there that satisfies this relationship. The distance from that to the center, times the distance from that to the center is the radius of this circle squared. So that's all that's saying right there, just giving us that basic, kind of the fundamental way we thought about inversion. So let's see what some stuff does. So let's just start with a point. I can move this and it's really nice. Notice that as the point I'm inverting, and
there's a symmetric relationship. P prime is the inversion of P, and P is the inversion of P prime. So that relationship goes in both directions. Here, I don't know if I can move that one. No, it only lets me move P. But notice that the further that outside point gets away from the circle, the closer the inside one gets to the center. And as we approach the circle, they actually merge the instant they touch the edge. And then they actually can change roles. If I just bring this one in, then the other one moves out. That looks a little janky, the way it's kind of, there's something a little, yeah, a little, it's a little fucked up, quite frankly. So, I don't know what's up with that. Let's clear that out. There we go. Let's take a look at the line and notice what its inverted image is. So one of your homework problems is take a line and find the equation of its inversion. And so you have the line, God, I don't know what it is. I forget what the equation of the line is. But you're taking that line and you're inverting it. So that line inverts into a circle most of the time. Let's see what happens as I move this line. Isn't that cool? Look at that. So the minute they touch, they agree at one point. And as I move this line into the circle, the image of the inversion starts to move outward. And as the line moves toward the center, that circle becomes bigger and bigger. And the minute that line I'm inverting goes through the center, its inversion is a line. I want to talk about that. Yeah, I mean, we've already agreed this thing's fucked up. But what happens when I invert that line? So I'm about to talk about that. Here's the center of my point, center of my circle, and I want to invert this line here. So what is happening? Why is the image still a line? Well, remember that inversions happen on a line through the center. So right now, if I take a point on the line and I ask for its inversion, it's going to be on the line itself because that's how inversions work. So if this is Z, Z star will be out here. Now what you're going to read about over the weekend, because I know you're totally going to read about this stuff over the weekend, and I trust you with my whole heart that you will do this. This point here, so remember how the closer we get to this, the further out the inversion gets? As we hit the center, that center point actually gets sent to infinity. So it's almost like this line, this half of the line is getting flipped around the circle. So the part that's out here, let's call it zigzag, and the part that's in here, dotty dot. When I invert this line, dotty dot is on the outside and zigzag is on the inside. So after the inversion, it looks like this. And it's actually completely reversed. And then the same thing goes down here. The line actually breaks apart during inversion. Where they're attached here, these two pieces come apart and then come together at infinity, which sounds insane, but it's true and it's beautiful. And the part that was at infinity, this line is out at infinity somewhere, this one's out at infinity somewhere. Those 2 points come down to the center of this one. And what's going to make this all make sense is when you start thinking about the complex plane as a sphere. This is the Riemann sphere. I'm just kind of priming your reading. And this is infinity at the top, and this is 0 at the bottom. And a line that looks like this is actually just a great circle. Think of a line of longitude on the globe. So that when you invert it, it just flips around like that. Howdy.
I thought this class was at 2:30 for some reason for that today.
It's all right, you had the exam. Your brain is a little drained.
It must be.
We're glad you're here. That's great.
So
That's great.
confused.
It's okay. Welcome.
Thanks.
Welcome to our new member, Tara. Okay, so. All right, let's clear this up and let's look at lines. So I guess the point that I wanted to make there was that the inversion of a line
is a circle unless that line goes through the center of the circle we're inverting. So what about circles? If I start with a circle out here, what happens as I move this toward? So first off, you see the red image is the inversion, and it's a circle. So the inversion of a circle is a circle until, well, here's an interesting thing right here. Look at this. Notice how the inversion and the circle become the same at that point? I mean, more or less, right? There's some error here in this thing. One of the things we're going to talk about today, hopefully, and certainly, if not today, by Monday, think about the tangent lines where these two are intersecting. So you've got that, and you've got that. And those tangents are perpendicular to each other. These are perpendicular to each other down here. At every other instance, they are not perpendicular. So notice right there, this blue line intersects the circle of inversion at a not right angle, and so does this one. And the two of these don't intersect at a right angle at all, right? That's a very acute angle, that's a very obtuse angle right there. What happens when I keep moving this dude? So at this moment, they become the same. Then as I keep moving, look what happens to the inversion. The minute the circle I'm inverting touches the center, its inversion becomes a line. So what's happening here is that this blue circle's the thing I'm inverting. I'm turning it inside out around this dashed circle. So what happens is, this point, and remember, inversions are always on a line, so I know that the center, its image after inversion is right here. This point here, you're basically dividing by 0, and so that point becomes the ends of this red line. So this part flips inside, and then these two ends break apart and meet out at infinity. And this intuition will grow as you do more work with this stuff, and then as I just keep moving it, it becomes a circle again. And then as the circle, I don't know what's happening there, that's just kind of cool. Just a circle, yeah, nothing interesting's happening. Ooh. Anyway, I sure like the zap. So let me just show you a polygon really quick. This is just cool. You can see the image of the polygon under inversion. Look how funky it gets inside there. Can you zoom in? Yeah, looks like a cop badge on the inside there or something. And see, everything is still a closed shape, and as soon as I actually cross that center, the inversion becomes an infinite beast and reaches out toward infinity. So, this is a good intuition to have. This is a great app to play with. Please play with this app. It's a good weekend. I mean, we're nerds, right? We like this kind of stuff. That's the end of the app show.
Do this with crossword.
Oh, well, what's that?
You can do it at the same time you do a crossword.
You can do it at the same time you do a crossword, yeah. I want to show you the other app that I would like you to play with this weekend as you do your reading. If you go to content, go to Riemann sphere. So this is what I've been talking about, and I might as well just talk about it a little bit more. The green thing is the complex plane. The red thing is the Riemann sphere. And so the way we think about the plane being wrapped into the sphere is that for every point Z in the plane, we draw a line between it and the North Pole. This is a unit sphere just sitting right in the middle of the plane. There's the top half above and the bottom half below. And so you draw a line from the North Pole to the point, and wherever that intersects that sphere, that's its new representation. So on the sphere, this Z is that point. Let me show you how else this might work. This app is pretty good because you can rotate and stuff like that. You get a sense of what's going on. And as I move that z in, notice how it's tracing a little trail on the complex plane. It's also tracing that on the sphere. So we can get that. Isn't that cool? That's just freaking awesome. Just beautiful stuff. And I think I can even zoom if I want. My goodness, yes I can. But look at, so what happens when you go to infinity? Let's move this point away. Notice how you're moving up the sphere. So check it out, I'm drawing a line in the plane. What is being drawn on the axis here? So see how there's a great circle kind of being drawn on the sphere? It's not a very good one. Let me try that again. Let's move this nice straight-ish line. It's really hard to do this in perspective. That's actually not bad. So you can see here that a line on the sphere is actually, oh, look at that. That looks like a black hole, right? The new way we understand black holes. But yeah, you can see that infinity then becomes this top point. Here's an interesting thing. That point is not, no matter what direction you head out in, you end up moving toward that top point. So this is looking really bad here. But what I'm trying to do is just move out and show you that no matter what direction I move outward in the plane, it's just moving toward the same point. And now I'm just kind of enjoying star shape. Okay. Fun stuff to play with. Good things for our head. Good ways to understand why I keep talking about infinity being a point and why our book will. So, enough of that. But please play with that. All right, I want to, so I was going to answer a bunch of questions, and I probably will be doing some on Wednesday or Monday, I guess. But I did ask you to do one thing for today, and I definitely remember that I asked about that. I was asking you all to read through a couple of sections, and one of the things I wanted to ask you about, and I'm still going to ask you, is, let me find it here, Corollary 329. And we're going to get there today, but I want to walk us there. So I want to take we're all going to grab hands, we're going to walk to this inversion of clines that are orthogonal to each other, orthogonal clines, something like that. So let's start off with this theorem 328. Actually, let's start off with lemma 327. So remember, a lemma is a tool for proving a bigger result. I am not going to prove this, but I am going to show you what it says. So the proof is just, the proof is very tedious. It's certainly not fun to go through together. It's not a good for a math party, really kind of thing. But the result itself is kind of cool. So if I have a circle of radius r, let's say center of C naught, radius r, little r, and I take a point outside the circle, P, out here. I'm going to call the distance from that point to the center of the circle S. So that distance there, we're going to say is S, whatever that length is. So in other words, S equals P minus the center, the distance between them, the modulus of that difference. Then I'm going to take any other line through P that intersects the circle. So draw some line from P that passes through the circle. Oh, I hate that line. I don't have a undo button, so too bad. And it's going to intersect the circle in a couple of points, M and N. So what this lemma tells us, and this was proven by Euclid. This is ancient shit. This is the primal geometries were done by Euclid and folks before Euclid. But what the result says is that if I take P minus M times p minus n, that is equal to the distance from the center to p, so squared, so s squared, minus the radius squared of the circle. So no matter where m and n are, this quantity remains constant. Notice this is independent of m and n. And so sometimes I wanted to talk about this because I wanted to show you what I would do to understand something like this. First off, reading the proof is invaluable. But when you get a result like this, start playing with it and looking for extreme cases. Try to gain some understanding of it. And so the first thing I would like to talk about is what happens, what is going on here when m and n are equal? In other words, when I've got a tangent to the circle. So what if m equals n? Let's just take a look at that for a second. I'm going to draw a new picture again because that's getting a little messy. So here's center, here's p. I've got the distance here from p to the center is s. I've got a tangent line that goes straight across and just nicks that circle at one point. We're going to say that's m and it's equal to n. And then I've got my radius right here. Can someone help me with some fundamental kind of geometry results here? Is there anything we know about this picture that we can add that's not stated? This is a line theoretically. What kind of stuff? Yeah, what are you thinking of?
There's a right angle.
Where at?
Where, like at the tangent line.
Right here. So, have you seen this result before? Should we talk about this? That any tangent line to a circle, so you take a circle and you make a tangent line, that is perpendicular to the radius at that point. So if I have an R and I have a line L, and this line is tangent to the circle, it's always orthogonal, the expensive word for perpendicular, the good mathy word for it. These two things are always orthogonal, no matter how this is sitting. So Lou is using that fact right here. So what theorems might help me here? What results come into play when I have a right triangle? Yeah, someone's gonna summon Pythagoras, but Lou did it for us. Pythagorean theorem. We've got a right triangle, my friends. You know this stuff. You're tired and you're unsure. That's a bad combo for getting group activity. So this is a right triangle. It's just this dude right here. Let's draw it out. I'm just gonna pull it away from the triangle. This is the point M or N. This is the point P, and this is the center. This distance is S, this distance is R, and this distance here is P minus M, which is also P minus N. So this theorem, in other words, when M and N are equal, these two things are the same, and I just have the Pythagorean theorem. So when M equals N, we just have the Pythagorean theorem. This is kind of an extension of that. Do you see this? Because, so this quantity here, if P and M are equal, let's just call it M. So I've got P minus M, quantity squared, equals S squared minus R squared. You just gotta rearrange things to see the Pythagorean theorem in this. Just shift that R to the other side. This is my hypotenuse. And these are just the two sides. This quantity here, this is called the power of the point. I don't know what the hell to do with that information. It's in our book. I was like, cool. Tried to play with it, tried to see why. Don't know why, but maybe we can talk about it. This is the power
of, ooh, I like that, the power of P with respect to C. Whatever the hell that means. How does the power change as the point P gets closer to the circle? What happens to the power as P gets closer to the circle? What is the power when P is on the circle? 0. S is the distance of P to the circle. R is, and once P is on the circle, S is the distance from P to the center of the circle. So when those two, when you're here, R squared is S squared, and so your power is 0. So I don't know, I guess the power becomes more as it moves away, which is a weird thing. I don't get it. So that's why I say I don't get what power is all about. But good news, we don't have to. So we'll never talk about it again. But we need this result to prove theorem 328. And that's what I really want to talk about. Theorem 328. We're going to kind of go through this proof together. We'll go through every proof together, but some are kind of important. So here's what's set up. C is a circle. Not surprising. Yes, right? Not a shock. I told you, I got this thing C, it's in geometry. What do you think it is? A line? A cline? It's a cline, it's a circle though. So, C is a circle centered at Z naught. I've got a point not on the circle. Let's call that Z. A cline through Z is orthogonal to C if and only if it goes through its symmetric image, Z star. So I'm going to write this up and then we're going to talk about it, because this is actually really important. A cline through, if I can spell, a cline through Z is orthogonal, there's that beautiful word again, to C. And we're going to talk about what that means, because you got to know what that means to even get anything out of this. A cline through C is orthogonal to C if and only if, and we probably should talk about that too, because that's a logic and proof kind of thing, it goes through C, Z star. And let's write out what Z star here is. Z star is the inversion of the point Z in C, and that's the notation of that. Invert Z in C, you get Z star. Okay, so let's make another little note here so that we write it and say it. Z star and Z are symmetric with respect to C. There's a lot going on here, quite a bit. Let's clear this up. Let me get you caught up. And I guess I'm going to ask someone if you could tell me what it means. Someone that's not Lou. Someone else could tell me what it means for two clines to be orthogonal, or what you think it might mean. So let's talk about this part right here. What does it mean for a cline to be orthogonal to another cline? What does that mean? This stuff's contained in the readings. We were getting, Nathan.
Would that be what you just said about right angles when they both?
Yeah, absolutely. So what does it mean for two circles? So I've got a circle C, and I've got another circle. What does it mean for them to be orthogonal to each other?
The intersection forms a right angle.
Beautiful, yeah, beautiful. So it's very nice. So I've got a C, and if I've got another circle, thank you, Nathan, that's beautiful. And I've got another circle D, and I didn't do it here, because what we want are their tangent lines to be at 90 degrees to each other, but if they were, and I'm just gonna pretend like they are there, if those tangents intersect at a 90-degree angle, then those things are orthogonal. So these would be orthogonal circles.
And then, you know, it also, once it's on one of those points, it's actually on the other. Let's talk about a few things here. Let's see if we can work our way through a few things. Let's start with circle C, because definitely C is going to be a circle for us here. In fact, they told us so. Could you take a minute and think about, I'd just like you to think about this, and let's come together. Here's a line L floating around in space. When is that line orthogonal to the circle C? Can you see, can you just take a few minutes and think about this? When would that line be orthogonal? Can you give me a condition that I could always check and go, oh yeah, that line is definitely orthogonal to the circle. So take a minute, please. What has to be true for a line to be orthogonal to a circle? Christian.
Gotta pass through the center.
Damn, I was gonna sit down. That was great, thank you for denying me my break. No, I'm just kidding. All right, so yes, that was so beautiful, Christian. Perfect. So it's orthogonal if the line goes through the center. If the line doesn't go through the center, it is not orthogonal. So that is a two-way condition. That's an if and only if. So let's just put a little note here. Note to selves. Note to selves, all ourselves. A line L is, and I'm going to show you a nice little symbol that I'll use. That's the perp symbol for perpendicular. Kind of says it all, right? Is orthogonal to a circle C if L, if and only if L passes through the center of C. Does if and only if need some explanation? Because not everybody's had logic and proof. Would anyone like me to explain when I say if and only if, what does that mean? Could someone tell us what that means? Someone who hasn't, and Nathan's done so much for us today, but he's going to do more for us. Go ahead, my friend.
I was gonna say that's the only option, I guess, like just if and only if. Is that what you're asking?
Yeah, it's kind of it. Yeah, it's kind of it. That's definitely. I like what you're saying because that's true. But Ella, you were going to say something.
Just that both parts of the statement have to be true. Like if it's an if then, like I don't know. I guess it's kind of hard.
No, it's cool. You're
But,
thinking in logic tables, right?
Yeah. Like in this case, the line is only perpendicular if it passes through the center, and if it passes through the center, then it's perpendicular.
Yeah, exactly. So that's exactly what we heard in several different ways, which is quite beautiful. It just means if I say this, if and only if this, it just means this implies this and this implies this. They are the same. It just means equals this. They are the same. You got one, you got the other, and you got it in both directions. Thank you, friends. That's very good. So notice over here, let's see, we have a cline. So they're saying the thing we're talking about could be a line or a circle. We know we're talking about a circle that we're reflecting in. Is orthogonal to C if and only if it goes through Z star. So let's see if we can just reason this through with a line. So we got a cline through Z, and let's just assume it is orthogonal, and it's a line that is orthogonal to the circle. So let's assume line L is orthogonal to C. We know from Christian's theorem that it must go through the center as well. So this is true if and only if L goes through the center. So this little double-headed arrow that I'm using here is if and only if. It's just my little shorthand for if and only if. It goes through the center. And that means that where this line touches the circle, we have a right angle. So what do I have to show? I have to show that for any z on that cline, so z is on the line L, how do I know z star is also on that line? Yes, ma'am.
Wasn't it given to us in a proof that z star is a constant times z?
Yes, exactly. Yeah, beautiful. Oh, that's a nice way to say it. Yes. Remember how we proved the inversion formula? We've said it a couple of times that the inversion is on a line through the center. So very nice, Kitra, thank you. That z star has to be on a line through the center. So L goes through the center, and this is true. Thus, if z is on L, by definition of inversion, z star is also on L. Because the inversion is always on a line through the center. And I don't want to we can get some nitty gritty about going the other direction, but does that sound pretty reasonable? Cool. So we'll start off with this line stuff because it's easy to see and easy to work with, and it's stuff we already know. So now it gets a little trickier. And we're going to assume we have a circle with the z on the circle. So now here's the thing we're inverting in. Here's C. We're going to invert in C. Here's its center, Z naught. I think they might call it O or whatever. We'll call it Z naught. And I've got a circle that's now intersecting this thing. And there is the point Z on the circle. So we've got a cline through Z. And I need to show that this intersection is 90 degrees if and only if the inversion of this Z is actually also on this cline D. So let's let D be a circle intersecting C. Let's label a few points here. I'll call that intersection point T. We only need one of them. We'll just kind of get him up there right away. All right, so let's let D be a circle intersecting D. And what do we got to do? If and only if it comes through. So what I've got to do is show that the inversion of the Z is also on D. Need to show that the inversion with respect to C of Z is on D. And what we need is that result. So let's draw some lines and stuff and get this picture going. And we're going to see some Pythagorean theorem stuff come in here again. So let me look at my notes because I've gone through this proof about 5 times to see if I can remember it. And okay, let's let O be the center of this guy. And I'm going to let S be the distance between these two centers here. So let S equal the distance from O to Z naught. That's the distance between centers. And then let's draw a line to figure out where the inversion of Z would be, right? So I start with the center, I pass through Z, and it looks like it intersects D at another point. Let's call that point P. My goal is to show that P is the inversion of Z. So let's got this. Let's draw a line from Z naught through Z, and note its intersection with Z, with D, as point P, or at point P. Yeah, all right, cool. So we need a few other little tidbits here. Let's say that the radius of this circle O is K, I guess they use in the book. That's weird, I don't use a lot of K's like that, but it's all good. So let's actually make a little note here. A circle intersecting D. Let's put a little note back here of radius K. Just to get that in there. All right, there's a lot of freaking lines drawn on this board right now. I think there's gonna be a few more before we go. So let me just refresh my memory about what is about to happen here. Well, we are gonna form, we wanna show that, okay, here's what we're gonna show. That this intersection is 90 degrees if and only if that point P is Z star. So, our goal, show the angle at intersection T is 90 degrees if and only if P is equal to Z star, the inversion of that Z right over there. There we go. Okay, so we gotta fall back onto that weird lemma we started with about the power of a point P. We're gonna change our perspective here. Instead of this being the circle that I'm talking about, I'm gonna think about this circle here. So let's refresh our memory about what that result said, but let's draw it in terms of D. So recall that if I have a circle D, and it's got a center O, and it's got a radius K, and I pick a point outside of that circle, well, here my point is going to be Z naught. So thinking back to that very first lemma that I referenced, we've got the distance between these 2 points being S. We've got a point Z here already on that circle. We're gonna draw a line from that. We already have that line through Z, and then we've got this point P up here. And I know that the distance between these two is just the radius of the circle, so that's K. Let me label these things a little bit better. So from lemma, whatever the heck that was, 317, probably 3.2.7. Is that right?
Yeah.
Thank you. From lemma 327, we know some things here. We know that Z minus Z naught times P minus Z naught is equal to S squared minus K squared. That's just from that lemma, and we're flipping our perspective up there on that picture. All right. So I'm just gonna make this little note down here, or just kind of summarize this here. I just wanted to show it. From lemma 327, we know this fact. Z minus Z naught times P minus Z naught, the distance, is equal to S squared minus K squared. Cool. Okay, so let's draw some other angles here. So now I'm gonna draw this line Z naught T and this line OT, and those are just the radii of the circles. This distance here is the radius R of our original circle C. Yep, it says that in the results there, I didn't say it on the board. But C is a circle of radius R. This one's a radius K circle. And when would this be a right angle? What would it mean for that to be a right angle there? Do you you see any triangles floating about? Yeah. If this is a right triangle, what does Pythagoras tell us? That this squared plus this squared is that distance squared right there. And so that's what we're gonna, that's part of the if and only if. We're gonna assume that's a right angle and show that that means this is Z star. And then we're gonna show that if that's Z star, then that has to be a right angle. And that's kind of the crux of this whole thing right here. So let's just hold off on that and let's make a little note to self. Because as you're doing proofs, you wanna make little notes to yourself, probably much more organized than this. I'm just kind of making little side notes that if triangle Z0 OT, ZOT, or whatever the heck that is right, how about this? Is right, sorry, if and only if Pythagorean theorem holds. In other words, and that is if and only if S squared, that distance between the centers, is equal to R squared plus K squared. Okay, and that is true if and only if S squared minus K squared is R squared. So here's what's going to happen. So let me get here, let you absorb that. The plan is to show that this quantity has to be R squared. And once we have that, we'll have what we need. Because if that's R squared, oh, yeah, here, we're almost there. We're actually right at the cusp. We just have to kind of pull these things together. So let's do that. We are right there, and I guess I can get rid of this because we've got it summarized. Okay, cool. Let me move this so I don't die. Okay, most things. Okay, so let's come back to this and say if P is equal to Z star, so like pull it together now. If P is equal to Z star, then equation star becomes, I'm just going to replace P with Z star. Z minus Z naught times Z star minus Z naught equals S squared minus K squared. So all I'm doing right now is saying, okay, let's assume this is Z star. And I rewrote this equation to get that up over there. What is the normal equation here? If Z and Z star, if this is Z star here, what is that relationship? And I forgot who gave us that a little earlier. Just think back to this circle now. Come back to C. If Z and Z star are symmetric with respect to each other, what would this equal? R squared, exactly. So if Z and Z star are conjugate, or not conjugate, if they are symmetric with respect to C, then this must equal R squared because Z and Z star are symmetric with respect to circle C, which has radius R. So that, what I'm saying then, is if this is actually Z star up here, then this quantity here, S squared minus K squared, must be R squared. So from this, we immediately get S squared minus K squared, which is always equal to, must equal R squared, and now we have the Pythagorean theorem holding. And we said that if the Pythagorean theorem holds, this is a right triangle, and the circles must be orthogonal. I spent a long time thinking about this shit, so I hope you're coming along with me. The part of it is just trying to like explain it in a way that makes sense. So I have to make it make a lot of sense to myself. Since the Pythagorean theorem holds at point T, we have a right angle. Cool. Okay, now the other direction. Oh yeah, hey Morgan.
What is that first word underneath the sentence that you just wrote? What is that first word?
Show me.
Since.
Since.
Okay.
Thanks.
It looks like SWOE.
Yeah, sure it does. I'm sure it looks like a lot of different things. Let me read that sentence again. Since the Pythagorean theorem holds at point T, we have a right angle. There. There's the sentence. The other direction is actually pretty straightforward. Let me just slow down just a little bit. So notice that what I did here was I assumed that if this was Z star, then this must be a right angle. I need to now assume that's a right angle, and so that must be P star. So let's go that route. I gotta leave up some things here. I'm gonna leave up that little buddy. So now assume we have a right angle at point T. So I got a good old right angle here. That means the Pythagorean theorem holds. We already talked about that. So thus, this means the Pythagorean theorem, let's just call it the PT, because I got a feeling we're going to use it a lot the rest of the semester. I've used it like 5 times today. This means the Pythagorean theorem holds for triangle Z0 T0. I'm just going in all sorts of different orders here. It doesn't really matter. And that implies that r squared plus k squared equals s squared, that distance between the centers. Cool. So, this thing here holds no matter what is happening. This is a universal truth no matter what the geometry of the situation is. So we're going to come back to that and compare it to this. Now we know this. So this implies that s squared minus k squared is r squared. Aha. So star, which is freaking right here, like magic somehow, I love it, star becomes a new thing. I'm just going to replace that with r squared. Z minus z naught times p minus z naught is equal to r squared. But that's the equation for reflection. This is the symmetric point equation right here for the circle C. So this, let's draw our picture out again. But this, you got to add exclamation points because this is, we're about done. But this is the symmetric point relationship for circle C. The inversion relationship for circle C. And the only point that P could be is Z star then at this point. So this must mean that P is symmetric to Z. This implies P is symmetric to Z. And that means, and there's only one symmetric point, that means P is Z star. That's just some weird ass symbol I wrote out of pure euphoria. I used to sign my proofs like that when I was a
weird deadhead math student back in the day. All right, thanks for bearing with me for that. You did well. Congratulations. I love you all for still being here, conscious now. There was some phasing in and out during that proof. I get it. So, what did we just prove? We proved this result that says, and I'm going to put it back up on the board so we can reference it, because now I have a question for you. And it's the last thing I have to ask of you today. Better be, right? Because we got to call it for class. So the result we had is this. A cline through Z not equal to the center of a circle is perpendicular, is orthogonal to C if and only if it goes through the conjugate point. I keep calling it the conjugate point, the reflection. So in other words, if I've got a circle here, and I know that this is a right angle, then every point Z that is on here also has its reflection in this circle C on it as well. So here's the thing I want to ask you, my friends, and it's the corollary without proof in this section. So here's what I'd like you to argue for me. Corollary 329. Inversion in a circle, in circle C, takes clines orthogonal to C to themselves. You remember when we looked at the app at the beginning of class and there was that moment when the inversion and the circle merged? That said that its inversion became it's itself. It is its own inversion. How does this follow from what we've just seen? Yes, I do expect sentience. Damn it. Can someone tell me? Can you think about that for a second? Because I had said, think about this between Wednesday and today. You may or may not have. I've got my suspicions. Lou.
So I mean, you're kind of looking at two cases. So if you've got the line and it's orthogonal to C, that means it's going through the original circle, right?
Yes.
And we know that those lines just basically flip themselves inside out and become the same line again.
Exactly. So can I draw what you just said, because that was beautiful. So Lou's saying that if I've got this point Z here and the cline that is passing through it is also passes through the center, make that, then we know that that is by nature perpendicular to that thing. And so when I invert this line, it just turns inside out into another line. The inversion of a line through the center is a line through the center. So awesome. You got the other one?
I think so.
Cool.
And then when you're looking at the circle, if they're orthogonal,
Yes.
that means that, right, so for any Z that's in that circle, it's going on to another point in that same circle. So all the inside points are just going to recreate that outside point.
Yes.
When you invert it, and all the outside just going to kind of come in and become inside.
Yes, perfect. So when I have a circle that is orthogonal to another circle, all of this circle out here just consists of the inversion, the pairs of points that are symmetric with respect to the other. So for every point here, Z, its reflection is on that. This circle out here is just built of pairs of reflected points through this one. And so when you invert this one, it just becomes that one. When you invert that one, it just becomes that one. When you invert these outside ones, like Lou was saying, they just become the inside ones, and vice versa, because they're already paired like that. spent a lot of emotional energy thinking about today. So I'm glad it's done. Please, start on the problems. You see me begging? It's gonna be on recording. I beg you to start on the fucking homework, please. Yes, ma'am.
I was just gonna ask about the homework, but
Oh, I love it. No, yeah, it's a great. Can you? Do you want to wait till after?
it kind of has to do with the bonus problem.
Ooh, I don't remember
Or the
what the-
one that's like, that was written wrong and then like something.
Oh
else.
Christ, yeah. Let's talk about that.
It's done, but I'm getting like almost the same answer as another one of them.
Yeah, I'll come take a. We'll look. We'll look together. That's cool. Awesome. Thank you, friends. You, my friend. Hi. Yes, ma'am. So quiz, awesome. I was just didn't know what R and Z not were. Just looking for little details, but otherwise quite beautiful. Thank you. I don't have a great.
No, I love him.
But I know you did. What's up with that? What happened?
Honestly, I don't know.
Do you have it, maybe?
Oh, I know it's in my
Yes.
room. It's sitting in my room.
Okay,
Like-
awesome.
I sent you a picture of it.
That's it. That's it. Okay,
Yes.
thank you. Cool. And I was
You
gonna
were like, I
collect
don't
the
remember what the
original.
grade was, and then I was like, I sent you a
Give me an
picture.
example.
Okay, thank you. I'll check that out. Awesome. Thank you, ma'am. And then there was that makeup from the.
Yes, I will get that to you.